Hi everyone, welcome back to Life Technologies YouTube channel, and thank you so much for watching and your continued support. So if it's your first time watching our videos or you've been watching our videos and you are yet to subscribe, kindly hit that subscribe button to support our channel and also to stay tuned for more upcoming videos. So this is another episode of our Huawei Lab simulation series. Remember, in this series we discuss how to operate, how to manage, how to configure and troubleshoot different networking protocols or different networking technologies on Huawei routing and switching devices. So if you are looking forward to learning how to manage, how to configure, how to use the CLI for Huawei routing and switching devices, kindly check out our previous episodes on this series. We also have another series demonstrating how to operate Nokia devices, and we have another new series that focuses on Juniper devices. So if you are looking forward to learning how to operate and manage different devices from different vendors, kindly check out the videos on our channel. So in this episode, we'll be focusing on how to apply minimum links feature on link aggregation to achieve traffic failover. So what we are looking at basically is how to use the link aggregation features. So we know that link aggregation is a very common networking technology that allows us to bundle multiple physical links into one logical links. So we could be having, for example, we could be having two physical links connecting two sites, and instead of having these two independent links operating individually, we bundle these two links into a logical group. And after bundling these two links into a logical group, first we have higher capacity because maybe we had one 10G and another 10G. Now we have an aggregated capacity of 20G, 10 plus 10. Or we could be having maybe two 3Gs or one, two 1G links or three 1G links. We can bundle these links into one logical group, and this is what we are calling the link aggregation group, the LAG. So when you're implementing link aggregation, the first thing is it's improving on capacity. It's increasing the capacity because you are aggregating from 1G to 2G or maybe two 10G links to 20G. Another thing that it helps us is to improve network redundancy. Remember, whenever there is a link, just one link going down in the lag, you still don't have any impact unless you have capacity issues. So the traffic is able to fail over to the other link that is still active. So I've said that this is a scenario based, and this is the topology that we are using. You can see that you have S100 and S200. So from S100 to S200, we have two connections. We have one connection between R1 and R5 that is 4G. So we are aggregating 4 1G links. And then we have three connections from R2 to R4. So this one will be making a 3G lag. The upper one will be 4G lag because it's 1G links. We are bundling them into one aggregation group to come up with a link that has a capacity of 4G capacity. So the scenario that we are looking is many times you find that in our service provider networks, we are dealing with multiple fiber providers. It could be dark fiber, it could be DWDM, or any other transmission mode. So with this link aggregation, we could be aggregating links from different providers. In this setup, for example, between R1 and R5, you have, assuming we have two providers, so we can have two links from provider A, and then the two lower links could be from provider B. So we have aggregated links from different providers to come up with a 4G lag. So assuming that there is a fault either on provider A or provider B's fiber, we end up losing two links from the ETH trunk and we remain with 2G only. So when there is a fiber fault on provider A, the two fibers from provider A will be down. And if there is a fiber fault on provider B, we also lose the two fibers and we only remain with two that will be up. So whenever you are having the two links down, the BGP will still continue to advertise routes and traffic will continue to use the 2G link that has low capacity whenever you have lost the fiber from either of the providers. So one thing that can be done, of course, is to shut down the BGP manually between R1 and R5 so that traffic is able to switch to R2 and R4. But this manual intervention sometimes it takes time, and maybe the one who is being called to handle this issue is not aware of such a link and is not aware of what he needs to do. So the best way is to use dynamic ways. We need a dynamic solution that is able to disable this link aggregation whenever we are losing the two ports or the two interfaces from one provider. So this is where we'll be using the minimum links feature. We'll be setting this link aggregation maybe to a minimum link of 3 so that whenever we are losing the 3 links, we lose the lag. It's like the lag shuts down because we are now below the minimum required links. And whenever the lag goes down, definitely we don't have connection between the two. So we end up, the BGP will be down, the BGP will not be established. So we stop advertising routes between R1 and R5, and the traffic will dynamically switch to use R2 and R4. And when the link restores between R1 to R4, if the link restores to to 4G links, or the 4 links are now fully restored, the lag will come up again and BGP will be established and traffic will be able to switch dynamically from the secondary link to the primary link. So I mentioned that we'll be configuring BGP between the different nodes and we'll be first doing the checks to see that the traffic will continue to flow on R1 and R5 even whenever we have lost 3 or 2 links. So this is the lab setup. To start us with, we'll start by doing the basic configuration, configuring interface IPs between different nodes, and then we do BGP configuration and we verify that our BGP sessions are up. And finally, we'll do a simulation to see how the minimum links feature works to help us to switch over traffic from one link to the other. So I'm logged into the nodes. So we'll start with configurations on R1. So the first thing that we normally do, let me undo terminal monitor. The first thing that we'll do is to configure the sysname. So we'll set the sysname to R1. And then we'll configure the interfaces in the link aggregation. So when you are configuring link aggregation, there are different ways, and I will be showing you the easier way of how to configure a link aggregation. So the first thing that we need to do is, of course, to interface eth trunk. So we can create an interface eth trunk. These are the eth trunk number from 0 to 63. So we'll be using eth trunk 10. So after configuring eth trunk 10, the first step that you need to do is to configure the mode. So once you've created the eth trunk, the next step is to configure the mode. So there are different modes. Many times we normally use the LSCP static mode. So once you've configured the static mode, there are two ways in which you can activate the ports within that eth trunk. The first one, it takes time. You will have to go under this interface, for example, interface gig 0/0/0, and then I need to run the command eth trunk 10. So I have added this interface on that eth trunk. An easy way to do this is to use the trunk port. So I will be under interface eth trunk 10. I use trunk port. So I can add the remaining two ports, trunk port gig 0/0/1, and then you use 2 0/0/3. So I will have added the 3 ports under that eth trunk. If we check the configurations, if I do display this, that trunk port is not there, but when we check display current configuration, you can see that the 3 interfaces have the command eth trunk 10. So we have added the 4 ports on that eth trunk. The final thing that we need to do is to now assign IP address. So interface eth trunk 10 IP address, we are using IP address of 10.10.10.2, mask is 31. So that is it. I'll quit, and then we'll configure the interface facing router 3. So we are using an Ethernet 00 and then IP address 10.10.10.1, mask is 31. So we have finished configuring the ports on R1. We'll move to R2. So on R2 we are doing the same, undo terminal monitor, system view, sysname R2. Then I'll configure interface it twang 10, same number. I'll configure the mode. So it's always advised that you have to configure the mode before you add the ports, because whenever you add the ports, you cannot change the mode for the eth twang. So it's always good that you start by configuring the mode, SCP static, and then now we can go to adding the ports. So this one is ports. We add the 4 ports in batch, 0/0/0. This one should be 3. So display this, we are good. I'll configure an IP address of 20.20.20.2, mask is 31. Display this. So if I display interface it's twang 10, you can see that the bandwidth is 4G. The current bandwidth is 0 because the eth twang is currently down. We need to configure the other side of the eth twang before it's up. So I'll configure the interface going to R3. Interface Ethernet 0/0/0. It has an IP address of 20.20.20.2, mask is 31. No, it should be .1. This is .1, mask is 31. Then we can now configure R3. So I will undo terminal monitor so that we have a clean screen when we are doing the configuration. Configure the sysname to R3. And then I'll create interface Ethernet 0/0/0. IP address will be set to 10.10.10.0, mask is 31. We also need to configure interface Ethernet 0/0/1, IP address 20.20.20.0, mask is 31. So we have finished configuring interfaces on R3. We can go ahead and configure the interfaces on the other routers, starting with R5, R4. Let's start with R4. So undo terminal monitor, system view, then I need to be configure the sysname to R4. After R4, we need to configure the interface it's twang 10. I'll configure the mode to same LSCP static. IP address should be 20.20.20.3, mask is 31. And finally, we can add the ports. So twang port gig 0/0/0 to gig 0/0/2. Display this, you have your configuration for the eth twang. The next thing is to configure interface facing R6, interface Ethernet 0/0/0. IP address, we can see the IP address, it's 20.20.20.4, mask is 31. Let me verify the configuration on R2 again. Because I've added, this is a 3 gig link, so we don't need this port to be undo eth twang, so that we only have 3 gig on R2 and R4. So if I display interface, it's trunk 10, you can see that maximal bandwidth is 3G. We'll move to R5 and do similar configuration and do terminal monitor. Then system views is name R5, interface it's trunk 10, mode LSCP static. Then I will assign IP address of 10.10.10.3, mask is 31. We need to configure the trunk port gig 0/0/0 to 0/0/3. Display these. There we go. Great. Then I will configure the interface going to R6. IP address of 10.10.10.4, mask is 31. And finally, we'll now configure R6. So R6, same procedure. We need to create interface Ethernet IP address. It's set to 10.10.10.4.5, mask is 31. And then interface, this is 0/0/1. IP address should be, and this is 20.20.20.5, mask is 31. So we finished configuring the interfaces. We can try to ping, for example, .4. We are able to try to ping .4. We are also able to. So after you have finished the basic configuration for the interface, the next step is now to configure BGP between the routers so that we are able to exchange the routes from AS200 to AS100. So I will start with router 3, or we start with router 1 as usual. So this router, its BGP AS number is 100. We'll just configure the normal IP before peering. So it's peer 10.10.10.0, AS number it's 100. And then another peer, it's 10.10.10.3, AS number, it's the external AS of 200. So display these. These are the configurations. On R1, we'll configure R2. So on R2, same BGP 100. We start by configuring the internal peer 20.20.20.0. We are using just the point-to-point connection. Then we'll configure our eBGP .3 AS number. It's set to 200. So that is it. We go to R3. So R3 BGP 100. We have peer to 10.10.10.1. AS number it's 100. We also have another external peer .1 AS number. It's also set to 100. So we check the BGP configuration. These are the BGP configuration. Display BGP peer. The BGP is still idle. It will take some time before it's established, but as we wait, we can move to R4. So on R4, BGP 200. First, we need to configure the eBGP. So it's peer 20.20.20.2. AS number it's set to 100. This should be 100. And then for our iBGP peer we set to .5. AS number is set to 200. So display this to verify that we have the correct configuration. Display BGP peer to see whether the peer is coming up. It's still idle. Let's check on R3 if it's up. So you can see that our peering on R3 it's now established, so it will take time for R4 to establish also as we configure R5. So it's BGP 200. We need to configure the ABGP 10.10.10.10.2 AS number, it's 100. And we also need to configure another peer 2.5 AS number, it's 200. Display these are the configurations. We finally need to configure R6. So R6 will have two internal BGP peering, 20.20.20.4 AS number, it's set to 200, and then peer 10.10.10.4 AS number is set to 200. Display this to verify the configuration. So we have finished configuring BGP. Display BGP peer. The status is still down. We can confirm on R4. R4 we have one that is up, the other one is still coming up, it's active. R5 display BGP peer. One is established, the other one is still coming up. Let's check on R1. Display BGP peer. We have two sessions established, so we wait for R6 to establish the two sessions. They are now established, so when we go back to R5, we expect to have two sessions. When we go back to R4, we also expect to, let me see, still have one that is down. Let's try to ping .5. We are able to ping, so we wait for the session. Let's verify that we have, this is R4 towards R5. Then we check R5. R5, we have misconfigured something. Undo peer 10.10.10.5. We need to peer with R5. This is R5. No, R5 is okay. We need to check on R6. So I will just return peer 10.10.10.5. S number is set to R4. Display BGP peer. We have two sessions established. R5, R6. Display BGP peer. We have, the other one is coming up. Let me check on R2. Display BGP peer. We have two sessions. R4 we have two sessions. R3 we also expect two sessions, and then R5 display BGP peer. So the sessions are up. R6 display BGP peer. We have two sessions. R1 we also have two sessions. So our BGP is running okay. So what we need to do now is to advertise a route. We'll be advertising a route from R3 to R6. And this route, so we are advertising this IP, will create a loopback 0 and then assign 3.3.3.3 mask is 32. And we also create an IP on R6 and advertise it into BGP. So let's start with R3. File quit, interface, loopback 0, IP address, it's 3.3.3, mask is 32, and then how do you advertise it? You just need to be under the BGP configurations. So it's BGP 100, then we use the network command 3.3.3, mask is 32. So we have advertised this route to BGP. When we check R1, we expect it to have display IP routing table. You can see that it has this IP, it's learned via iBGP. We can do the same on R6. So on R6 interface loopback 0, IP address 6.6.6, mask is 32, quit BGP 200, network 6.6.6, 32. So on R3 and R5, display IP routing table, have these two, 3.3.3 and 6.6.6. When you check on R6 display IP routing table, you can see that you only have 6.6.6, you don't have 3.3. So display BGP routing table, you see that yes, you have 3.3.3, but it's not installed. The reason is the next hop is set to 10.10.10.2. So normally when you're advertising a route from IBGP to another IBGP, you don't change the next hop. So we need to configure these boundary routers to be the next hop self or the next hop local. So we'll start with R5. Let's start with R1. So R1, we need to make it, when it advertising the routes to 10.10.10.0, we set the command next hop local. And then on R2, we'll do the same, BGP 100 peer 20.20.20.0 next hop local. Then on R5, we do the same, peer 10.10.10.5 next hop local. On R4, we also need to do the same, 20.20.20.5 next hop local. There we go. So on R6, if we check the route, it will take some time to update. Display IP routing table, still don't have it. We give it some time for the BGP update messages to be exchanged between the peers. Now you can see that we have the route. So if I display BGP routing table, you can see that it's the best route and it has two next hop. So it's going via the upper path as expected. So on R3, we expect also to have display BGP routing table. You have the two routes. If I display IP routing table, let's check the BGP routing table. Display BGP routing table 6.6.6. You can see that we are preferring the upper path because of the router ID. So this one has a lower router ID. But of course, whenever you can use BGP attributes to achieve whichever path you want to make the primary or the secondary. You can use local preference, you can use AS path, you can use MED, any that is familiar to you. So after we have done this, you can see that we are able to ping from R1. So I will do from R3 to R6, I will do a continuous ping. And I will source, given that we have only advertised the loopbacks, I will source from 3.3.3. I'll put a count of maybe 10,000, and then I need to ping 6.6.6. So the ping is continuous, and whenever we do a packet capture from this link, we should be able to start packet capture. You can see that we have ICMP messages. Let me see, ICMP. So we have ICMP messages. When we do a packet capture on this link, we don't expect to have any packet drop, any ICMP package, because they are using the upper link, the primary link. So what happens when we have, for example, when I shut down, as of now, we don't have the minimum link configured. So whichever the case, whenever we are getting routes from the upper path, the traffic will still continue to flow using the upper path always. Even if there is only one link that is active in this link aggregation, all the traffic will go via the upper, the primary path. So what we want to do is to now log into R1. So if I log in, let me log into R5 instead, and display interface it trunk. It's trunk 4, it's trunk 10. You can see that we have 4G link there. The bandwidth is 4G. So what I will go ahead and do is to shut down some links. So I will do interface. First I need to quit interface gig 0/0/0. If I shut down this link, now we expect the int trunk to have only 3G, trunk 10. You can see that the maximal it's 3, current is, the maximum is 4, the current is 3. The traffic is still passing through the upper path. Another thing that we can see the display BGP peer. Our BGP is still established, no problem. The next thing that we do is to shut down another link. So we say that whenever we lose 2 links, interface gig 0/0/1, I will shut it down. If I display interface it's trunk 10, you can see that now the maximal is still 4, but the current is 2, so it's decreasing. So if you are pushing more than 30 gig of traffic on this link, it means more than 20. It means your traffic will be congesting, and you will have service degradation from AS100 to AS200. And even when we shut down the third link, maybe for example we make it 1G, still the traffic will continue to flow from R1 to R5 because BGP is still preferring that path. But what we want is whenever we have 2 links down and whenever we have only 2 links active in this ETH trunk or this link aggregation group, we need to be able to shut down this ETH trunk, and the traffic should be able to switch to the secondary path and use R2 and the link between R2 and R4. So what I will do is I will now go to this interface ETH trunk 10, and we can set the minimum links to 3. So when we set the minimum links to 3 and currently we only have 2, definitely the ETH trunk will be down, BGP session will be teared down, and then traffic should switch to use the link between R2 and R4. If you check our packet capture, let me see the pings from it was from R3, you can see that our pings are still going through. And if we are switching using the minimum links, remember this one will be non-service affecting. The traffic will switch seamlessly. You may just have maybe 1 or 2 drops, but we don't expect any drops. So from here, what I will do is and when you are configuring the minimum links, it's always good that you do it from both directions. So we can do it on R1 and R5 also, so that it's merging both ends of the ETH trunk. So I'll go back to R5, ETH trunk 10. You have this command list active number. When we set it to 2, you can see that our ETH trunk will still be up. Interface ETH trunk 10. Can see that our ETH trunk is still up, no problem. I need to do the same on R1. So I'll quit interface ETH trunk 10, list active links to 2. We don't have any issue. Display interface ETH trunk 10. The link is still up. So the next step is to now let's make it 3, so that whenever we lose 2 links and we are only remaining with 2 links which are not able to sustain the amount of traffic that we are pushing from site from S100 to S200, we want this traffic to fail over to the secondary link. So what I will do from R1, I will set the list active links to 3. And when we do this, if I display interface ETH trunk 10, you can see that now the state is down, and we expect traffic to switch from the primary link to the secondary link. So when we check our ping from R3, you can see that our ping is still ongoing, no problem. We haven't lost any packet so far. We only lost one packet when the traffic was switching from. So without any manual intervention, our traffic has been able to switch from the primary link to the secondary link because we have lost two links between the primary link that we have between R1 and R5. So we expect to be getting packets on this is, let me quit this and then we do another capture here just so that we start capture. We have the ICMP packets passing through via this link. The traffic has switched. So what happens? You can see that the physical links are still up. Our BGP, we expect it to be down. So when I log into R1 or R5 and display BGP peer, you can see that our BGP session is idle, but the physical links display interface brief. You can see that the two physical interfaces are still up, but they are not taking part in any routing. So if I restore one link, on this eth trunk, maybe 0.0.0, display this, the link was shut down, undo shutdown. We expect first the eth trunk should restore. So display interface eth trunk 10. You can see that now it's up and its current capacity is 3G. Display BGP peer. It's still not established. We give it some time so that our traffic is still on the primary link. Until the BGP is established, then the traffic should be able to switch dynamically. So BGP is established. You can see this link, no packets. But on this side, we can now capture the packets because traffic has switched and it's now using our primary path. So we are able to achieve the traffic switchover using these minimum links feature of link aggregation groups. If I can restore the other link also, we shut the links on R5. If I display interface, it's trunk 10. Still have one link shut down, interface gig 0/0/1. Display this, undo shutdown. So we now back to the 4 gig link. It's trunk 10. So yeah, you have seen that we are able to display BGP peer. Our BGP session is up and now traffic is flowing using our upper path from R6 using this way and also this way, because now we have 4 links that have restored and we have set the minimum links to 3. So whenever we lose 2 links of the links in this link aggregation, we end up shutting down the eth trunk, and then traffic is able to switch from the primary link to the secondary link that is between R2 and R4. So this is a good application. This is a scenario based. This is a really case troubleshooting scenario that we've done, and it's a good thing that you can try to see how you can use it in your network to be able to dynamically switch the traffic. Because if we don't do this, it means first we need to increase the capacity between R1 to R5 from both vendors, so that when we lose one vendor, we still have enough capacity on the other vendor. And remember, that one comes at a cost. Or the second thing is to do manual interventions, so that whenever we are losing 2 links or 3 links between R1 and R5, we manually shut down this link unless we have some kind of monitoring, some kind of automation that is able to monitor this link, then you are good to go. You can use automation to monitor this link, and whenever you were losing some links, then you switch the traffic dynamically to use R2 and R4. But using the minimum link, these are soft application. It's a good application that you can use in such a scenario to achieve the same objective without doing any manual intervention or without having an engineer logging into the network and do some manual switchover of traffic, because you end up losing some traffic while you are doing the manual intervention in the network. So I hope you've enjoyed this session. I hope it has been useful. And just a reminder that please remember to subscribe to our channel for more upcoming videos. I will be sharing more scenario-based, more real-life applications that we are using in the service provider network, just to help you understand what is really running in the service provider networks. So remember to like this video, to leave a comment, and also to share with your network. And again, just remember to hit that subscribe button and stay tuned for more upcoming videos. Thank you.